Today, I'm going to talk about Quantum for Bio. As you can see, it's a 50 million supported challenge to accelerate quantum technology in healthcare. It is a program that is offered by Wellcome Leap. So I'll spend some time on what Wellcome Leap is. So Wellcome Leap is an organization, a non-profit organization that launches bold, high-risk programs on a global scale in order to accelerate or in order to increase the number and speed of breakthrough in human health. In the last 5 years, it has launched 12 programs, 620 million at work, in 28 countries. On the bottom, you can see the programs, and you see I'm going to talk about this program, Quantum for Bio. So a feature of Wellcome Leap's program is it focuses programs at certain use cases. So this diagram is showing you there are type of program or funding or research that you can do. The x-axis is showing use cases or innovation. The y-axis is showing the quest for fundamental understanding or basic research. We found that most often breakthroughs are created by fundamental understanding-based research who are driven toward use cases or use-inspired research. This is what we call research in Pastor's quadrant, and Wellcome Leap tries to launch researchers in that quadrant. So how Q4Bio is related to that? So this diagram kind of sums it all. On the x-axis, we are showing the number of qubits, and on the y-axis, we are showing program depth or how much computation you can make with those qubits. This shaded area on the bottom left that you can see, these are the capabilities of existing quantum systems that we have. If you try to match them on that figure, it's kind of these are research geared towards innovation. Upper right of this figure, you see the existing quantum algorithms that we have. And you see they are very far up and right. We don't have the necessary qubits, necessary depth to run them. But they have increased our fundamental understanding. And if you try to match them on the other figure, it's kind of a basic science. So how can we bridge this gap? How can we make sure that these two researchers combine to develop something in the Pastor's quadrant? And this is why this Q4Bio challenge was launched. The challenge goal is simple. Can we develop quantum algorithms that will work with near-term computer together to solve a human health problem? This was the challenge, and we asked the participants to come forward and participate in this challenge program. We have put aside $40 million as a support for whoever taking part in the challenge. And that is why we call it a supported challenge program. It's not a simple challenge program where you do something and we give you money. We are also giving you the support of $40 million to take part in this challenge. There is also prize money. If any team can achieve this challenge within that target resource that is defined here, you get a grand prize of $5 million. There are multiple $2 million prizes if you can demonstrate scalable solution that will eventually get to that challenge. So this is, in summary, what is the Quantum for Bio challenge program is. By the way, the clock is still at 20.
Okay, so you still have 20 minutes.
Yeah, I still have 20 minutes? Good. So this is, I tried to kind of explain what the Q4Bio challenge program is. This is a 30-month challenge program. We started on September 23. We are going to end on March 2026. We divided these 30 months into 3 phases. Phase 1 is 12 months. The core challenge or the core task of this phase 1 was identify relevant biological problems that might benefit from quantum computers. Develop near-term algorithms that you think you can run in near-term computers. Do resource estimate, do feasibility analysis. All this was done in phase 1. It was 12 months. We started with 12 teams. Each team had been funded up to $1.5 million. After the phase 1, There was elimination, selection, and we moved to the next phase with only 8 teams. And in the phase 2, it was basically about doing HPC simulation of your algorithm to verify their feasibility for the next phases, do all the things necessary to choose your hardware, whatever it takes. We paid each of these teams up to 750K, and there were only 8 teams. The duration was 6 months. And then there was another elimination round. We moved to phase 3. We are currently in phase 3. And in this phase, we have 6 teams. Each of the teams are going full on to implement their algorithm on a quantum hardware. And in this phase, each of the teams are getting up to $2 million. So this is where we are currently now. I'm going to talk about the results and update from each team. And these are all the teams, the 6 teams. But I want to note, each of the team has a combination of expertise of at least 3 disciplines. Because of the challenge itself, this team needs expertise from quantum software, quantum hardware, and also from the biology angle, right? So that these 3 can talk, they come in a common platform and go towards the challenge. Let me start with the first team. It composed of algorithmic, expertise from quantum algorithm, IBM, they are providing expertise on the quantum hardware, and Cleveland Clinic, the bio expert. Their goal is to unlock scalable quantum simulation for PDT drug discovery. We know PDT, you inject a patient with photosensitizer molecule, then expose them to light, and they start to react, and they basically kill the tumor. The challenge is designing a very effective photosensitizer molecule, or more specifically, designing or estimating the excited state property of large photosensitizer molecule is classically very difficult. And this is where they think quantum computer can actually create value. So in the last 24 months, they have worked a lot of things. And at this moment, I can say this kind of framework has been developed. It will start from a molecule that you want to estimate. The end goal is to calculate desired property. It will start, there will be some pre-processing steps, then there is the quantum computer, and after that, the data from the quantum computer would be post-processed to get to your relevant desired property that you need. 2 important things I want to mention in this case. One is they have developed a very novel tool that kind of does the ansatz construction and the necessary steps classically. We know normally in VQE we have to do a lot of research, spend a lot of research to do this kind of thing, and it takes lots of quantum resource. But they have bypassed that part and offload those parts into a classical simulator that tries to do everything classically in polynomially scaling way. And then another part is they are doing the quantum simulator or quantum hardware experiment in IBM quantum hardware. And the data that is being generated, the noisy data, is being post-processed. And they have developed another novel tool that they call quantum boosted DMRG. It basically takes the noisy data from a quantum computer and then it puts it in a DMRG framework which uses novel innovation in order to enhance the quality of the data, right? So together, they actually try to do it. And a great feature of them is all these parts, they are not optimized in isolation. Each of them take care of what is happening after the quantum computer, what is happening in the total framework, and it's a total optimization of all those tools. And so far, they have been able to demonstrate an end-to-end demonstration of this full framework to simulate excited state property of their photosensitizer molecule for up to 52 qubits, right? And their plan is to increase this by the end of the program to 76 and then 100 qubits. Now comes the question of, is it actually going to lead to quantum advantage? Let's say on the right side figure, if we try to solve this same problem classically, let's choose DMRG, right? We will start from a molecular property, we will end to some desired property that we want to go. This is actually a benchmark that has been done, and the figure is shown in the bottom. On the x-axis, it's showing you the active space, how much electron or qubit you are including or orbital you are including in the active space. And the y-axis is showing the increase in bond dimension. So if you look here, up to 70 or 80 qubits, you can see with number of increase in qubits, your bond dimension scales exponentially. After certain part, if you include more orbital in your active space, then it raises sub-exponentially. So I can say if I want to solve this problem through DMRG, the state-of-the-art classical methods, we can solve it either with polynomial complexity or exponential complexity. On the other hand, their framework, the whole thing has the option actually to solve it polynomially. So if we look at the first portion of it, the classical problem is actually scaling exponentially, but their method has a promise to solve it polynomially. This is for a particular orbital size and for a particular error that we want to achieve, right? So this is kind of a result that are showing us how we can actually go and how we can achieve like quantum advantage type of advantage or value. Okay, let's go to the next one. Because of time, I'm not going to be talking in detail about all the programs, but this is another performer of our program, Stanford, NASA, Brown, with others. And their goal is to leverage near-term quantum computing and machine learning to simulate ATP hydrolysis problems, right? So it is known that cancer cells depend on ATP hydrolysis for their sustainable growth, right? And a deeper understanding of this issue would allow us to build therapeutic design. And this is where this team thinks we could include the techniques in quantum chemistry and leverage and connect them with machine learning capabilities in order to develop real results. So this is the second team also working on the drug discovery. And so far, they have been able to demonstrate first of its kind molecular dynamics on an actual quantum simulator. Let's go forward. The third team, Harvard, MIT, Quera, they are also working on drug discovery using programmable quantum simulation with a focus on antimicrobial drug design. And their research is divided into two thrusts. In one thrust, they are trying to use quantum simulation for binding energy affinity calculation. At the same time, they're trying to use quantum simulation to effectively learn about how NMR protein design or how we can determine NMR protein structure. And the unique thing is they are using the neutral atom quantum computer, and whatever algorithm they're designing is not going alone. It is being informed by that structure and the structure of the quantum hardware that they have. So together they're kind of doing a co-design in order to reach their target. This is the fourth team, Nottingham, Facecraft, and Quera, and they are trying to address a neuromuscular disorder called myotonic dystrophy. It is a real problem. 1 in 8,000 people are affected, and no cure is available. But the good thing is they have identified the target protein in order to solve this problem, and a class of inhibitor molecule has been identified. But the difference from this team to the previous teams are, instead of trying to go through the wave function solution way, like solving the Schrodinger equation, they are actually trying to use quantum computer to boost the performance of DFT, density functional theory. So we know density functional theory is one of the most widely used tool or framework for chemistry, material science. And it in fact earned the Nobel Prize in chemistry. But what they are trying to do, they are trying to use a quantum computer, and using this quantum computer, they are trying to calculate the exchange correlation functional of the DFT, which is the main problem of DFT. And when they found the exchange correlation functional, they will feed it to the classical loop to boost the performance of DFT. And of course, they are going to use this data to train a machine learning model. So together with quantum and machine learning, they will get a very efficient exchange correlation data that will boost the performance of DFT. And so far, this is their roadmap. They started emulating the smaller molecules. They started with lithium hydride and slowly went above increasing in scale and size, and they generated data, and they have basically created a database that was based on systems, more than 70 systems, and all this data, this accurate quantum data, have been used to train a neural network and a machine learning model, which is then used in the classical DFT loop in order to increase the performance or boost the performance. Their planned experiment is now underway with up to 256 qubits in a Quera computer. So that is their goal. So I guess, yeah, this was the fourth team. So these four teams were working on drug discovery problem. Now let's go to the fifth team. This is the team composed of Oxford, Cambridge, and Wellcome Saginaw Institute. What they're trying to find applications of quantum computing in pangenomics. What is pangenomic? Pangenomic is the study of the entire set of genetic information of a particular species. It is very important to understand how disease develops, how a particular species evolves, how diversity is affected, and those kind of things. So the problem is, if you try to solve this kind of problem, these are very, very complex optimization problem. And if you try to solve them classically, there are separate regions in human DNA that are so variable that you cannot accurately solve them classically. They become inaccurate. And those are the regions that they attempt to solve through these quantum computing methods. So far, they have done very good, they have achieved very good progress. So the first progress is on the encoding and loading side. If you want to do what you want to do in genomics, you have to first load this data into a quantum computer. You need encoding. They developed efficient machine learning based encoding, efficient state preparation method that allows them to load data efficiently into a quantum computer. And their result, so far they have been able to load some smaller molecules into a quantum simulator. This is a specific example. So this is called 5x174. It's a single-stranded DNA organism whose data actually has been loaded into a quantum simulator. And this is very, very significant milestone, because in the 80s, this was the same molecule whose DNA was loaded into a classical simulator that earned the Nobel Prize in chemistry. And 50 years later, through quantum 4-bio program, this becomes the same molecule. This is the first time somebody is loading this thing into an actual quantum simulator. And because of time, I have to skip these parts. This is another team, Inflection, MIT, and University of Chicago. They are trying to develop quantum biomarker algorithm that will help us in achieving or bypassing some complexity that classical algorithms cannot do. But let me skip this one. So this is my last slide. So I should change this one. It's not over the past 18 months. It should be over the past 24 months. So what has been achieved through this Q4-bio program? It was originally launched to improve the quantum algorithm part, which have been achieved. But another thing that achieved that we did not anticipate, the task of fitting those whole pipeline into a near-term quantum computer actually enforced them to develop tremendous classical improvement that we actually did not anticipate it before. And the third thing is, in order to create value, generating the science in an isolated section, it's not enough. You have to innovate, and all those innovations needs to work together in a coherent form, in a coherent framework, so that you can actually create your science and translate it into something that has a value. And through Q4-bio program, we have this kind of framework, this kind of workflow that didn't even existed 18 months ago. And we believe these workflows are here to stay. With time, they will be addressed, edited, innovated in order to address future health needs. And this is what we feel will be the lasting legacy of Q4-bio. So to summarize in this talk, I tried to show you what Q4-bio did, how Wellcome Leap is tried through its own capacity to catalyze the application of quantum algorithm in human health. And this is the takeaway message I would like you to take away from here. Thank you so much.